Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. We'll begin with a discussion of electrostatics. The fundamental problem of electromagnetism is to determine the force that some charge Q experiences in the presence of a system of other charges. Now that force depends on not only the distance between the charges, but also on velocity and acceleration. We're going to begin somewhat less ambitiously here. We're going to just focus on those systems where the force depends just on the distance between the charges. So in other words, where the charges can be considered stationary. That's what I mean by electrostatics. There are three observations, experimental observations, that underlie all of electrostatics. The first one of which is that there are two charges, positive and negative. Second observation is that the force depends inversely on the distance between them, and it's an inverse square law, in fact. And the force acts along the line joining the two charges. The third and final observation is that the force is also proportional to the product of the charges, and that the force is attractive if you have unlike charges, and it's repulsive if you have like charges. Those three experimental observations can be embodied in Coulombs Law. We'll be using SI units, so in other words, forces in units of newtons. Notice that we have proportional to the two charges, Qi and Qj. It's inversely proportional to the square of the distance between the two charges. And the charges will be attractive, or rather the force will be attractive if we have unlike charges, and will be repulsive if we have like charges. Let's suppose that we have a system of charges. Not just one, we've got Qi here, but we've got a whole bunch of other charges, Qj. How do you calculate that? Well, it's also an experimental fact that that force, the net force acting on Qi, can be written as a summation of the force on Qi due to this charge, this charge, this charge, this charge, and so forth. So in other words, force on charge Qi is equal to the force due to charge 1, force due to charge 2, and force due to charge 3, and so forth. And that's a summation I equals 1 to n, where n is the number of particles in the system of Qi, Qj times the separation vector Ri minus Rj over 4 pi epsilon naught. Epsilon naught represents the permittivity of free space and has value 8.854 times 10 to the minus 12, and over the magnitude of the separation vector Q. So in other words, separation vector Ri minus Rj cubed. Let's consider an example. Let's suppose I've got some charge, capital Q, and it's surrounded by 8 charges, equidistant away. And let's suppose that those charges are placed at angles 0 degrees, 45 degrees, 90 degrees, 135 degrees, and so forth. And you could do the math. You plug all the write this in terms of cosine, sines, and what have you. Do the math and come up with an answer. But a better way of looking at this is to notice the amount of symmetry in the system. I've got a charge Q over here, but I've got one on the left-hand side, an equidistant array. I've got a charge Q up here, distance A away, but I've got a charge Q below it. So what happens is that the net force on charge Q is just equal to 0. You'll find that when you start working more and more problems, you have to make use of the symmetry of the problem in order to solve it. It might not just be a question of saving yourself some grief with the algebra. Might be a question of being able to solve it in a timely fashion as well. Let's look at a variation of this problem. Got my same charge Q, and this time I've got seven charges. I've removed the charge that's at the 90-degree position, and I want to figure out what's the force equal to. Well, once again, you can plug all those forces in here, calculate them explicitly, but you can make use of the superposition principle in the fact that, well, this system is actually the same thing as my initial system where I had the 8 charges. If I happen to add a negative charge up here, if I add these charges to this one, then I have Q minus Q at the same location. Not physically, of course, but we're doing this mathematically. That's equal to 0. So that's the same problem as right here. Well, I solved this problem where I had charge Q surrounded by the 8 charges, and I figured, well, that's equal to 0. So now my problem just really boils down to figuring out the force that this charge minus Q exerts on the center charge. We'll assume here that this is the z direction, goes up and down in this case. We have Q times minus Q times 0 minus a z caret. So 0 is the position of my charge Q, capital Q, and minus Q is that position az. There is capital Q times lowercase q, all over 4 pi epsilon naught a squared in the z direction. So this charge Q will experience a net positive force on it due to this configuration. As it turns out, we're actually going to be working problems more in terms of the electric field than dealing with force, because it just problems are easier to handle that way. And then going a step further, we'll introduce electric potential, which makes the problems even a little bit more readily handled than the electric field. Okay? So let's define the electric field. Electric field is defined as the force over some test charge. And to make this expression a little bit more precise, we're going to take the limit as the test charge goes to 0. And the reason why you're going to do that is because you don't want the test charge to influence the original system of charges, the electric field of which you're trying to determine. So in other words, by taking the test charge equal to 0, it's not going to change anything in what you're trying to measure. So this is, we take the limit as qt goes to 0 and say, okay, now we can determine what our electric field is as a function of position. I have a system of point charges. The electric field due to those is equal to summation at I equals 1 to n, where n is the number of charges, qi times r minus ri. R is the field point or observation point. That's where you're calculating your electric field. Ri represents the source point, or where the charge is located. All over 4 pi epsilon naught, magnitude of the separation vector cubed. Now, although I didn't write it down explicitly, it is also the case that the electric field obeys the superposition principle. So in other words, you can calculate the field due to one charge another charge, and so forth, and add them up to get your net electric field. Let's look at a particular problem. Let's say we've got 2 point charges. Q and minus Q, and let's suppose that they are equidistant away from the midplane, or x equals 0. And I want to determine the electric field due to these 2 charges. And maybe we'll call that y for now. Okay, so electric field at any point in space is equal to Q times r minus a in the x direction over 4 pi epsilon naught r minus a in the x direction cubed minus q times r plus a x direction all over 4 pi epsilon naught r plus a in the x direction cubed. So we're taking the magnitude and separation vector in both cases. I want to know what the electric field, though, is along the midplane. We are doing this in SI units, so force will be in units of newtons, any distances will be measured in meters, charge in coulombs. The electric field can be written in units of either newtons per coulombs or volts per meter. It's 6 1/2 to 7 of the other, but generally speaking, most people use volts per meter. To find the electric field along the midplane, that means we're interested in finding out what's the electric field when x is equal to 0. And there's your electric field. Since the denominators are the same in both cases, I can simply add up the numerators and I'll see that the y and the z components cancel out. At any point along x equals 0, the electric field is directed to the left. Electric field lines are very useful for visualizing electric fields. And be aware when you see any diagrams of this kind, it doesn't mean that the electric field has the same magnitude everywhere. The electric field line just gives you the direction at a particular point in space. So if we took isolated charges, first of all, your electric field lines radiate outwards, like so. If you have negative charge, the lines terminate there. So this is a source, and this is a sink. Electric field lines never intersect each other, so they radiate outwards and starting positive, going negative. And they look like this. Let's consider a system where you have two positive charges now. And I want to answer the same questions before. What's the electric field due to these two charges? Everything is the same as before, except now I've got a positive sign there instead of a negative sign. I wanted to figure out what the electric field along the midplane was. Again, or let's say just at the origin, wind up with zero. Using the same kind of analysis as before, the electric field lines radiate outwards, but they cannot intersect. Determining a negative charge, however, there are no negative charges in this case. So if I just start close to the origin, or rather I should say, I start close to each charge, they're going to radiate outwards, but if you get further away, what you'll see is that the charge, the electric field lines go like this. So there's kind of a bunching up, if you will, of field lines because they cannot cross, but they start at the positive charges and go off to infinity. Now let's look at some problems that involve continua of charges. And I'll reset to give myself a little bit more room. Let's suppose that you've got a line charge. This integral, or the summation rather, is going to become an integral. In that case, you're going to integrate over the length of the wire, whether it be a straight wire, curved wire, what have you. If you happen to be given a surface charge distribution instead, then the integral will be a surface integral. least if you happen to have a volume charge distribution. Then you'll be calculating a volume integral. From now on, whenever you see an unprimed R, that means the field point or observation point. That's the point at which you're calculating the electric field, or when we get into electric potentials, that'll be the point at which you calculate the electric potentials and so forth. The primed quantities represent the sources, the locations of the sources, okay? So we're integrating over primed quantities and winding up with an expression for the field in terms of the unprimed quantities. When you're tackling these problems, the first order of business, of course, is to determine what dimension problem do you have. Do you have a line charge problem? Do you have a surface charge problem? Or a volume charge problem? Lambda here represents the line charge density, sigma represents the surface charge density, and rho represents the volume charge density. And notice that I've written those densities as functions of prime. Generally speaking, these quantities will depend on position, but for the problems that we do for the rest of this lecture, there won't be any dependence on position, and they'll just be constant values that can plot on the integral. The next question is, what coordinate system do you use? Now, when you were in general physics, you just use Cartesian coordinates. You'll find that when you start using things like cylindrical coordinates and spherical coordinates, that makes the problem a lot easier to handle than before. So, first question, what dimension do you use? Second question, do you use Cartesian, cylindrical, or spherical? Notice you have R prime vector inside the integration sign. In Cartesian coordinates, vector R can be written as x caret plus y caret plus z caret. In cylindrical coordinates, the vector R can be written as s, where s is the distance from the axis in the s direction, or radial direction, plus z in the z direction. Now, because this quantity here, this unit vector, generally speaking, depends on the position in space, you can't, generally speaking, pull that out of the integral and do the math. It's almost always a better idea to write the vector R using cylindrical coordinates, but sticking with the Cartesian unit vectors, because x, y, and z unit vectors are fixed in space. So you can pull those out of the integral and not have to worry about making some kind of mistake there. And spherical coordinates. R sine theta cosine phi in the x direction, plus R sine theta sine phi in the y direction, plus R cosine theta in the z direction. Okay? So determine how many dimensions your problem has, and number two, decide on a coordinate system. Problems that we actually can handle using these integrals is limited. We investigate problems that are line charges, charges that exhibit cylindrical symmetry, problems that exhibit spherical symmetry, and so forth. So if you want to investigate the electric field due to more complicated systems, you're probably going to have to resort to numerical techniques. Well, let's take an example. So I want to figure out what the electric field is due to a line charge at the midplane. First order of business is to determine what dimension problem we want to do, or we are doing. Well, you're talking about a line charge. It's basically a wire, so that's clearly one dimensional. We'll be using that first integral. Next order of business is to figure out what coordinate system to use. That problem undoubtedly looks familiar to you from general physics. Now, when you did general physics, you worked everything in Cartesian coordinates, most likely. I'm going to work this problem in cylindrical coordinates. I will choose my line charge to lie along the z-axis. And I'll orient it such that its origin is at z equals 0. And I'll further assume that the line charge is uniform, so instead of being a function of position, it's just lambda. Since I'm evaluating it at the midplane, that corresponds to z equals 0. And I'm going to do this in cylindrical coordinates. And remember, the variables I use when I'm going to integrate over will be in cylindrical coordinates, but I'm going to leave the unit vectors, or write the unit vectors, in Cartesian vectors. So in other words, x caret, y caret, and z caret, if it were non-zero. Our prime in this case is just the source point, or source position, if you will. And since the wire lies along the z-axis, r prime is equal to z prime z caret. Separation vector is s cosine phi in the x direction plus s sine phi in the y direction minus z prime z caret. I want to know the magnitude as well, so that's the square root of s squared cosine squared phi plus s squared sine squared phi plus z prime squared. Make use of the trigonometric identity that cosine squared plus sine squared is equal to 1. And so these two terms simply add up to s squared, and altogether we have square root of s squared plus z prime squared. I'm going to plug this into this expression. The limits of the integral are minus L over 2 to L over 2. We're integrating over the z prime coordinates. We have lambda over 4 pi epsilon naught out front. I'm going to evaluate the z direction term first. That term goes to 0. So what you see is that along the midplane, the electric field is going to be pointing either in the x, y direction or some combination thereof. And y terms give rise to non-zero contributions, so you'll have s cosine phi in the x direction plus s sine phi in the y direction, all over square root of s squared plus z prime squared times z prime over s squared. Now we just need to evaluate this at minus L over 2 and L over 2. And also I am going to replace this cosine phi in the x direction plus sine phi in the y direction by s caret. So I have s times s caret up there. And s squared over L squared, s squared plus L squared over 4. Another s squared in the denominator. These two terms will add up. And I'll wind up with an L. The electric field will point radially outwards from the line charge. It's useful to consider what the electric field line due to an infinitely long line charge looks like. So in other words, what if L gets very, very large? In that case, this s squared term is negligible in comparison. So basically you're going to wind up with an L over a square root of L squared over 4. Which is just L over 2. So this L cancels with this one. And that's the electric field due to an infinitely long line charge is equal to the line charge density lambda over 2 pi epsilon naught s. That's the distance away from the line charge, and that's in the s direction. Okay? Just leave it up there for one more minute and move on. Now, the next couple of problems, I'm not actually going to work them out, but I will set them up. Let's say that you have a ring charge, or a charged ring if you prefer. And in this case, your ring charge carries uniform charge density lambda. And you want to figure out what's the electric field along the z-axis. And you'll notice that whatever textbook you happen to be using, that you'll usually be asked to calculate the electric field along the z-axis for some of these more complicated configurations. And the reason why is because the math gets just a little bit too onerous. So we want to figure out the electric field along the z-axis. So I'm going to place, or along the axis of the ring. So if I place the ring in the xy plane, I want to figure out the electric field along here. It's a one-dimensional problem, so you're going to use this expression. In this case, you're going to be integrating around the ring, so dl prime is actually equal to r d phi prime. And you'll be integrating from 0 to 2 pi. Write out an expression for your observation. It's just going to be in the z direction. R prime, you want to write out an expression for any point along this ring. Let's say that you have a surface charged disk. characterized by surface charge density sigma. Once again, you'll be asked to calculate the electric field along the z-axis. And my disk looks an awful lot like the ring I've drawn. In this case, you'll be using the second expression. If you want to know what the electric field is along the axis of the disk, you want to place your disk in the xy plane and then evaluate it, or set r equal to z caret r prime. In this case, or let's talk about the a prime. In this case, you're going to be integrating not just over angles, but also over the radius as well. So in fact, that's going to be r prime, dr prime, d phi prime. And what are your limits of integration? Well, 0 to 2 pi, and also out to the radius of the ring. What's r prime equal to? Well, just write it out in cylindrical coordinates. And knowing that the disk lies in the xy plane, so the z component of this will vanish, and you'll just have an x and y component. Okay? So that's how you tackle those two kinds of problems, and using cylindrical coordinates as opposed to Cartesian coordinates. The next problem I'm going to work out all the way. So let's get straight to that. Let's suppose that we have a conducting sphere. Of radius r, and it bears uniform surface charge density sigma. So even though we're talking about a sphere, something that occupies a volume of space, I am going to use this third expression up here for calculating the electric field. What coordinate system do I want to use? Well, it's a sphere, so I might as well use spherical coordinates. In this case, because we are just on the surface of the sphere, the radius is going to be capital R. Sine theta prime, cosine phi prime. Now let me move over a little bit more to the left so I have more room. I have r sine theta prime cosine phi prime in the x direction, plus r sine theta prime sine phi prime in the y direction, plus r cosine theta prime in the z direction. Now, what do we want to evaluate? Well, your first inclination might be, well, I'll just write this as r sine theta cosine phi, blah, 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 so forth, okay? But as it turns out, this is symmetric. So why not just evaluate on one particular axis and then generalize results after you've done the integration? So I'm going to evaluate the electric field along the z-axis. So in other words, z caret. And therefore, my separation vector is equal to minus radius of the sphere times sine theta prime cosine phi prime x direction minus radius of the sphere sine theta prime sine phi prime y direction plus z minus r cosine theta prime z direction. Let's take the magnitude. Magnitude gives me square root of the sum of the squares. So I will wind up with r squared sine squared theta prime cosine phi prime squared plus r squared sine theta prime squared sine phi prime squared plus z minus r cosine theta prime squared. Notice these first two terms have in common the factors of r squared sine theta prime squared. So therefore, you look at those last two, it's just cosine squared plus sine squared. I can use that trigonometric identity. Cosine squared plus sine squared is equal to 1. And I'll have r squared sine squared theta prime. Now I'm going to multiply this final, or the last term out. It'll be z squared minus 2zr cosine theta prime plus r squared cosine theta prime squared. Once again, I have two terms that have a common factor of the radius of the sphere squared. I have sine squared, sine theta prime squared, cosine theta prime squared. Those two add up to 1, and I am left with r squared minus 2zr cosine theta prime plus z squared. Since this sphere is uniformly charged on its surface, I can pull sigma out. I integrate theta prime from 0 to pi and phi prime from 0 to 2 pi. We also have d phi prime in here. Okay? So all I'm doing is I plug in for the separation vector and put it in the numerator. So that's this here. And in the denominator, it's the magnitude of the separation vector cubed. So it's this term cubed. Okay. So first order of business, what do I integrate over? Well, so it turns out it's easier to integrate over the phi coordinate first because you'll notice there's no phi prime dependence in the denominator. Therefore, for these first two terms, you're integrating essentially cosine phi prime from 0 to 2 pi, and you're integrating sine phi prime from 0 to 2 pi. Well, that goes to 0. So these first two terms contribute nothing, and you'll just be left with a z component when you evaluate the electric field along the z-axis. So this is sigma. I can pull the z caret out for 4 pi epsilon naught. I'm going to pull the r squared out. And remember, your surface element looks like this. Okay? So when I do the integration, there's no phi prime in this last term, so that just gives me a factor of 2 pi. Okay, so we've got these constants out front. We're integrating from 0 to pi of sine theta prime d theta prime. Z minus r cosine theta prime in the numerator. In the denominator, r squared minus 2zr cosine theta prime plus the z squared all in the 3/2 power. Turns out it's useful or convenient to make a change of variables. So I'm going to set cosine theta prime equal to u, and therefore du is equal to minus sine theta prime d theta prime. And that will also change my limits of integration from -1 to 1, but because of this negative sign here, that will be -1 to 1. This is sigma z caret r squared over 2 epsilon naught. just do the math here, work out the integral yourself, or what I prefer to do is just look it up in a table. And when you do that, you'll see that this is equal to ZU minus R all over square root of S, R squared minus 2ZRU plus Z squared, evaluated from -1 to 1. Okay. First term is going to give me Z minus R, and that is going to be absolute value of Z minus R minus Z minus R all over Z plus R, absolute value. Now it makes a difference whether we evaluate the sphere inside or outside, so let's take inside first, Z less than R. If that's the case, this first term is going to contribute -1. Second term is going to contribute +1. And that's equal to 0. So we come up with a remarkable result that even though there is surface charge on the exterior of the sphere, the electric field inside vanishes. And what you'll see in the kind of examples that we work through, and especially with Gauss's law, that the electric field inside of any conductor in electrostatics vanishes. Outside, of course, it won't. If Z is greater than R, this is just going to be 1 plus 1 is equal to 2. Well, that 2 cancels this one, and I actually left off one factor here. There should be a Z squared in the denominator here as well. So let me just write that in before I go any further. Okay? So anyway, when you integrate this, you have ZU minus R all over Z squared, square root of R squared minus 2ZRU plus the Z squared. So can't leave off the Z squared there. Okay, so this will be sigma R squared over epsilon naught Z squared in the Z direction. It's convenient to write the surface charge density in terms of the total charge. So this is charge spread over a surface area of 4 pi r squared. I mentioned at the beginning of this problem, it's convenient just to evaluate the electric field along the z-axis rather than some arbitrary point, because this is symmetrical. So if this is the magnitude of the electric field in the z direction, well, generalizing that, the magnitude of the electric field is q over 4 pi epsilon naught r squared in the radial direction. So basically outside, it looks as if all the charge were concentrated at the center. It looks as if there were a point charge at the center of that sphere, okay? So the important results here, inside the sphere, the electric field vanishes. Outside, it appears as if all the charge were concentrated at the center of the sphere, okay? When we get into Gauss's law, this problem is much easier to handle. You don't have to worry about doing all this messy integration or losing track of certain variables, okay? Okay, so there's one other problem that you might want to try out for yourselves. Instead of taking a conducting sphere with a surface charge density of sigma, try out a uniform charge density. So in other words, instead of having sigma on the surface, you'd have a volume charge density rho, uniform. And instead of handling a surface integral, you'll be handling a volume integral. Outside, you'll wind up with the same result. It will look like all the charge is concentrated at the center of the sphere. Inside, of course, the electric field will not vanish, and I will leave that to you to figure out. Okay? So anyway, that concludes the lecture on Introduction to Electrostatics.